In the last several videos, we looked at different aspects of NMR data that are useful for determining the molecular structures of organic molecules. We also, in earlier units, focused on IR and MS as additional techniques to provide information about molecules on our pathway toward determining the complete structure of an unknown compound. In this video, what we are going to do is apply the understanding that we gained from those videos to take data and use that data to determine the complete molecular structure of an organic molecule. You can find the example problem that we are about to work here by going to the Chapter 13 NMR handout, which is available under the Chapter 13 module on Canvas and also in Canvas under Files. So please take a look at that, and we will go ahead and get going on determining this molecular structure. So we're provided three main pieces of information. We are provided with the proton NMR spectrum, which you can recognize down here at the bottom of the screen because the units here are ppms and the axis range is reasonable for that of NMR, which generally starts at 0 ppm and goes up to a max of 14 ppm. Since we've cut off the spectrum here at 3 ppm, you can assume there's nothing further downfield in this spectrum. We also have the IR spectrum that we can recognize here because the units listed on the x-axis are wave numbers. That is in inverse centimeters. And we additionally have the molecular formula that was established by high-resolution mass spectrometry, HRMS, and low-resolution mass spectrometry, LRMS. So with these three main pieces of data, the molecular formula, the proton NMR spectrum, and the IR spectrum, we are tasked with determining the complete structure of this organic molecule. In the last video, we went through some general guidelines and a workflow for determining the organic structures using spectral data. The first step of that was finding the molecular formula, which we were given. The second step of that was to determine the number of rings and pi bonds in the molecule by finding the index of hydrogen deficiency. So that's what I'm going to do here in this workflow, applying the strategies that we talked about in the last video. The number of rings plus pi bonds is equal to 2 times the number of carbon atoms, so 2 times 5, plus 2, plus the number of nitrogen atoms, which is 0, minus the number of hydrogen atoms, which is 10 in our molecular formula, minus the number of halogen atoms referred to as X, which is 0. Divide all that by 2, and that will give us the sum of the rings and pi bonds in that molecule. So when we do this equation, we get 2 in the numerator divided by 2 in the denominator, which gives us an index of hydrogen deficiency of 1. So what that indicates to us is that the structure that we draw has to have 1 ring or 1 pi bond. So I'm just going to jot that down to remind myself that the final structure we draw has to have 1 ring or 1 pi bond. And I'm going to highlight that just to give myself that reminder. So that's the main piece of information that we can directly glean from the molecular formula. The other thing we'll keep in mind with the molecular formula is that when we finish solving the structure of this, it better have 5 carbons, 10 hydrogens, and an oxygen, or we've done something wrong along the way. Now what we are going to do is simultaneously explore the IR spectrum for key functional groups that we can spot, and the NMR data to stitch together all of the atoms present within this molecule. Taking a look at the IR spectrum, what you'll want to ask yourself in this IR spectrum is, do you see any functional groups peeking out at you? The two main types of functional groups that we can spot easily, or should be able to spot easily in IR spectra, are hydroxy groups, which show up as broad signals, kind of tongue-like because they dip down and they're very broad, that show up in this region around 3,000 wave numbers, depending upon whether that hydroxy group is part of an alcohol or part of a carboxylic acid. We see no evidence for a broad tongue-like signal here, and so what that tells me is that there are no hydroxy groups present within this molecule. We can also look around 1700 wave number for a strong signal that would be diagnostic of a carbonyl group in an aldehyde, ketone, ester, amide, or other type of functional group. And indeed, looking at the region around 1700, we see here at 1716, labeled here, we have the strongest signal in the spectrum. It's a very deep signal, which is very diagnostic of carbonyl groups because carbonyl groups are usually the strongest or close to the strongest signal that we see in the entire spectrum, and they will be at that range of around 1700. And so that indicates to us that we have a carbonyl group within the structure of this molecule. And I'm going to highlight that so that I keep that at the forefront of my mind. And if we have a carbonyl group, as our evidence supports here, that would indicate that the one ring or pi bond that we had within the molecule is calculated is that carbonyl group. And so I am anticipating that the final structure we draw had better have a carbonyl group. Now, in order to determine where that carbonyl group is at in the molecule relative to other atoms in the compound, we need to go ahead and take a look at our NMR data. The three pieces of information that we will always focus on when looking at NMR data is the chemical shift. That is where the signals are at along the x-axis, because that gives us an indication of how close those particular protons are to an electron withdrawing group. We will also look at the integral for each signal. That is, what is the area under the peak, because that indicates how many protons make up that signal, telling us whether it's a CH3 group integrating to 3, a CH2 group integrating to 2, or a CH group integrating to 1. And then the third piece of information is for each signal, we can look at the multiplicity or the splitting pattern. That is, how many of these little subpeaks are present within each signal, because that indicates the number of vicinal hydrogens, the number of hydrogens that are on the adjacent carbon using the n+1 rule. So looking at our NMR spectrum here at the bottom of the screen, the numbers that we see listed in blue represent our integral values. So if you see above a signal a number listed, that number indicates the integral of that. So I've highlighted all those integral values in yellow. So what we see is that we have 4 different sets of protons here. And we can anticipate, since if they equate to a single signal, that means all of these protons are equivalent. So if we have 2 equivalent protons, that is generally a CH2 group is the most common way to come up with 2 protons that are in an identical chemical environment so that they give a single signal. 3 is generally a CH3 group, 2, generally another CH2 group, and 3 is an additional CH3 group. Looking at these integrals, the integrals that we have determined here should add up to the total number of hydrogens present within the molecule. So if we take 2 plus 3 plus 2 plus 3, that equals 10, which indeed matches up with the molecular formula that we were given. That is a must-have because we have to see that these protons are all present. So now that we have laid them out as predicting that we have 2 CH3 groups in the molecule and 2 CH2 groups in the molecule, we need to figure out how those are all stitched together and related to one another, and where they are at in the compound relative to the carbonyl group that our IR supported. So thinking about that, we need to sketch out some possible ways that the atoms are connected to one another using the multiplicities that we have in our NMR spectrum. So taking a look at this, I like to start sketching things out at an end of the molecule, at a terminal, at the left terminal or the right terminal of the molecule. The nice thing about methyl groups is that the methyl group has to be at a terminal of the molecule. It has to be at one end of the molecule or another. And so we have within our NMR data here 2 methyl groups, a methyl group at about 2.1 ppm, here that I'm circling with my laser pointer, another one at about 0.9 ppm that I'm circling now with the laser pointer. And so we can predict that those are going to be the end points for the molecule. So what I am going to do is pick one of those two methyl groups at random and start working inward from there to try to piece together the structure of this molecule. So I'm going to go ahead and start with the methyl group that is at 0.9 ppm. So I'm just taking this CH3 group, sketching it out and label it as 0.9 ppms, and putting the term T there to remind myself that that is a triplet. So we ask ourselves, what would we need to do in order to have a methyl group that is a triplet? In order for a methyl group, the CH3, to exist as a triplet, the triplet term implies that this set of protons must be vicinal to two other protons, because remember that a triplet using the n+1 rule means that n+1 equals 3. So solving for n must equal 2. And so that means there are two hydrogens that are vicinal to this CH3 group. So I'm going to plug in that I anticipate that this CH3 group is adjacent to a CH2 group, because that is how the CH3 group would be able to exist as a triplet, is that it has to have these two vicinal hydrogens. So then we look at the rest of the NMR spectrum and we say, are there any CH2 groups? If so, where are they at? Well, we have one that is present here at 1.6 ppm and another that's present over here at about 2.4 ppm. So we have to ask ourselves, which one of those CH2 groups is the one that we are plugging in here in our molecule? And we can determine that by trial and error or process of elimination. So as we look at the two CH2 groups, the one at 2.4 ppm here is a triplet. Since this is a triplet, that means that this particular set of protons has to have just two vicinal protons, because two vicinal protons plus 1 would give that multiplicity of 3. In the case of the CH2 group that we have plugged into our hypothesized structure, there are at least 3 vicinal hydrogens, and so there's no way that this most downfield 2.4 ppm signal can correspond to the CH2 group that we've sketched out in our structure and read up here, because the multiplicity doesn't work out. In order for this CH2 group to have a multiplicity of 3, that means it can have only 2 vicinal hydrogens, and it already has 3 from that CH3 group. So therefore, the CH2 group that we are looking at here must be the one that is at about 1.6 ppm. So I'm going to sketch in that this is at 1.6 ppm. And the signal that we see here definitely exceeds a quartet, which is what we would predict if the only vicinal hydrogens to the CH2 group were the CH3 methyl protons. We would expect the signal for this CH2 group to be a quartet, applying n+1, where n is equal to 3, plus 1 makes 4, which is a quartet. This signal, though, exceeds a quartet, which means there have to be additional hydrogens that are vicinal to this CH2. And the way that we can accomplish that is by plugging in another carbon into the chain and attaching vicinal hydrogens there. So by process of elimination, if we have used the triplet methyl group here, that was the one that we assigned as the far left terminal of our molecule, we also already accounted for the CH2 group right here at 1.6 ppm. And we said that that CH2 group was going to correspond to our signal down here, which appears to be 1, 2, 3, 4, 5, 6. It appears to be a sextet. It has 6 of those subpeaks going on. That means that it needs to have 5 vicinal hydrogens. And in order for the CH2 group that we have measured here to have 5 vicinal hydrogens, we have 3 from over here. So we need 2 to be on the other carbon right here. So now, with it drawn out like so, this CH2 group has a total of 5 vicinal hydrogens. 3 over here, 2 over here, 3 plus 2 makes 5, which is our n number. n+1 makes 6, giving us the sextet that we see here, this complex multiplet of 6 subpeaks, which we have superimposed an enlarged version of just above the axis of our NMR spectrum just to make it easier to see. So be aware that this, what I'm highlighting with my laser pointer, corresponds to what you see below it. It's just an enlarged version so we can make out the multiplicity there. So therefore, I infer that this CH2 group, the next one in the chain, has to correspond by process of elimination to our group that is at 2.4 ppm. So I'm going to put a check mark on the group that is at 2.4 ppm and label that in here as 2.4 ppm. Also, to check my work, I'm going to go back one step to this CH2 group in the middle here and label that with its multiplicity, which we said was the 6 peaks, which we call the sextet. So we come over to the next spot here. This CH2 group that we recognize by process of elimination as having to be the one at 2.4 ppm right here. That is a triplet. And in order for this CH2 group to show up as a triplet, that means that it needs to have 2 vicinal hydrogens because 2 plus 1 makes 3. And indeed, it already has the 2 vicinal hydrogens right here on this adjacent carbon. So therefore, with this CH2 group being adjacent to another CH2 group, it is a triplet. And so that means that adjacent over here in this position that we haven't filled in yet, there can be no vicinal hydrogens there. So what could there be instead there? Because we aren't at the end of the molecule yet, and we need to plug in additional atoms. So we have to think about what we have available in our puzzle set that we could plug in here. So what we have available left in our puzzle set is we have a CH3 group that we saw in the NMR spectrum that we haven't accounted for yet, the one that's at about 2.1 ppm that I'm circling here. That will not fit in here because that would terminate the molecule if we plugged a CH3 group in right here. And moreover, the multiplicity of our CH2 group would not be able to be a triplet if we plugged a methyl group in here. So what else do we have? Looking at our NMR and our IR data, what we have left over to plug in and puzzle pieces that we haven't yet used are the carbonyl group that we saw by IR. And so what I'm going to do is plop in a carbonyl group right here. So if we plop in the carbonyl group right here, that will enable the CH2 group that I'm highlighting right now, the one that we saw was at 2.4 ppm in a triplet, that would allow that signal at 2.4 ppm to be a triplet because it has just 2 vicinal hydrogens. The carbonyl being adjacent to it is going to make sense because as we look at the trend of the ppm values, we see that the most downfield signal here at 2.4 is the one closest to the carbonyl, where the carbonyl oxygen is very electron withdrawing, so that's going to pull this signal for our CH2 downfield relative to the next signal, which is more upfield at 1.6 ppm, and then the methyl group is the most upfield at 0.9 ppm. So the trend is that the further away we get from the electron withdrawing oxygen, the more upfield those signals become. And so that all so far adds up and makes sense. We need to complete the end of this molecule by using all of the NMR data that we have available and making sure that we've accounted for all of the atoms in the molecular formula. And so in order to do that, we have one signal left here. It is a 3 hydrogen singlet rather. And where can we plug that in? Well, we can plug it in right here, adjacent to the carbonyl on the other side. I'm now highlighting that methyl group that we just plugged in. That is our methyl group that was a singlet, which I'm going to abbreviate as S, at approximately 2.1 ppm. And that fact that this signal is also relatively downfield compared to the other signals in the spectrum suggests to us that it is adjacent to the carbonyl group, much like on the other side, the CH2 group that's pretty downfield was adjacent to the carbonyl as well. And so with that, I'm going to put a check mark to indicate that we have accounted for that CH3 group singlet. We know it's a singlet because there are no vicinal hydrogens. And now with this, we have accounted for each and every atom within this molecular formula. Because if we look at the molecular formula for this, we find that it's C5H10O. So checking our work, it makes sense that our molecular formula syncs up with the structure that we've proposed in terms of the number and type of atom. We have accounted for our IR spectrum because in our IR spectrum, we said there was a carbonyl group. We've accounted for that here in our structure. So the IR data check out. Number of rings and pi bonds, check out, because we had 1 ring or pi bond expected, and we have 1 pi bond in our molecule here. So that's good to go. And then finally, we come down to the bottom of the screen here, and we have our NMR spectrum. And the NMR spectral data makes sense in terms of the chemical shift corresponding to how upfield or downfield a signal is based on the presence of electron withdrawing groups nearby. The integrals make sense because they integrate to the appropriate numbers for CH3 and CH2 groups. And the multiplicities make sense based on counting the number of vicinal hydrogens. We could additionally validate our information by comparing the chemical shifts that we see here to those present in the chart of expected chemical shift values, and we would find that each of these values corresponded very nicely with the values that were empirically determined and presented in the handout for chapter 13, where we were looking at expected and predicted chemical shift values for different types of groups. So if you look at the data for ketones, you would see that our groups here adjacent to the ketone very nicely fit with the expected range of protons that are adjacent to ketone groups. So with that, we've solved the complete structure of this 4-carbon ketone named 2-butanone by evaluating the IR, mass spec, and NMR data and applying that to infer the structure of this molecule. If we've done this correctly, all of the pieces of data add up and make sense perfectly. If we've done something wrong along the way, there's going to be some bit of the puzzle that doesn't exactly make sense, like a multiplicity that isn't quite right, or a chemical shift that makes no sense, or IR data that are not in alignment with the structure. So that's what you'll want to check, as we did at the end of this, is make sure that all of the data that you have go along with the structure that you've created. If there's things that don't quite add up, it means it's time to go back to the drawing board and trial and error your way through the problem from some other direction.